Sounds good.
Okay, hello everyone. Thanks for tuning in. Today we're very happy to have Shira Chapman from University of Amsterdam, who's going to tell us on the complexity of black holes. One quick remark is that we want this seminar to be as interactive as possible, so please make sure you ask questions whenever you have any. Thanks. Shira, take it away.
Thanks a lot. So yeah, very happy to be here. Yes, and indeed I like a lot of questions, and I do have a small screen showing at least the room in which you guys are, so no excuses. You can even like point your hands and I will see you. All right, so what I'm going to talk about today is going to be a set of ideas that came up in the context of ADS-CFT correspondence, which relate gravitational problems to measures from quantum information theory. And in particular, I'm going to focus on the idea that the geometry behind the horizon of a black hole is encoded in a quantity that is known as a quantum computational complexity. And the idea that quantum information measures are related to geometric quantities is not new at all. It's old. It dates back to the Bekenstein-Hawking formula that relates the entropy of a black hole to the area of its horizon. And more recently, I think you all know, we had very big successes using the Ryuta-Kainagi formula, which claims that the entanglement entropy, so basically the correlations between a region of the system and the exterior, is encoded in some set of minimal areas in the bulk, and that led to many interesting developments, including ANC theorems, including some studies of thermalization, chaos, scrambling, etc. And also in addition to better understanding of the holographic dictionary, which regions in the bulk are related to which regions on the boundary and the other way around. So the next station in the story is the idea that the interior of black holes keeps growing for a very long time. And the reason is that although from the outside, black holes look kind of stationary spheres or look of constant size, from the interior, the space keeps stretching towards the singularity in a sense that I will define better a little bit later. As a consequence, basically the interior of the black hole keeps growing in time, and that raised the following puzzle of how this growth is encoded in the boundary. And that's the thing that led the high energy community to study the idea of quantum computational complexity, which was proposed by Susskind as the quantity at the boundary which encodes this growth. So these are very general words. Before I move to more explicit details, I should say that I've been working on this subject for about 4 years now with many collaborators. Some of them are actually you. So I have a very nice map of all my collaborators, and you can locate some of you here. So yeah. All right, so that's the structure of the talk. I'm going to start with an overview. I think this way I will try to go a bit fast because many of the things some of you already know. I will define complexity and say a few things about its properties. Then the second part will be about complexity in quantum field theory, both for pure and some results for mixed states. And the last part of the talk is going to be about some ideas from holography, about the time dependence of complexity, and explaining how complexity is expected to react to perturbations. All right, so first thing first, I always like to start with the definition. So what is complexity? A complexity is a property of a quantum state, which is defined as the minimal number of simple unitary operations that one has to put together in order to construct the state that we are interested in, starting from a very simple unentangled reference state. And the best way to break it down, or the best understood example, is the one of complexity of spin chains. So there, for example, one starts with a reference state, which is a simple state with all spins pointing up, and starts applying a simple universal gates to construct a quantum circuit that we might be, that we are using to build the state we are interested in. Now, simple gates means that they are acting on a small number of qubits, and universal means that they can approximate any state that we are interested in. On the right, you can see an example of the universal set of gates, which includes both gates which act on a single spin, called phase and Hadamard gates, and gates that act on two spins, known as, for example, C0 gates. And this set is universal in the sense that it can allow us to get as close as we want to any state that we are interested in. Now, the point is to build a target state, so the state of interest, by applying a sequence of those gates, one after the other. And in many cases, when discussing spin chains, since the gates are discrete, it's not really possible to get to the state of interest, but only to get to a certain distance from it. And this distance can be arbitrarily small, but then as a part of the definition of complexity, we need to put this distance. How close do we want to get to the target state? Finally, with all these components, the complexity is the minimal number of gates that is required to accomplish this task. So for example, you can see in this picture, if I want to construct this state, I need to put at least 3 gates together, and so the complexity will be 3. Now, a very common complaint is that the complexity depends on the various choices that I make in defining it. So it depends on the choice of gates, it depends on the reference state, but certain properties will be universal, and I will mention that. But I think that more than this, it is more correct to think about complexity as a family of measures rather than a single measure. And simply, like the Renyi index as like the Renyi entropy as an index, and the complexity as, say, indices for various different definitions of complexity, which are the gates and the state I start with, etc. And one last thing is that this notion, of course, came from the world of quantum computation, which uses quantum superposition to perform computations in parallel. And so in these cases, the really hard problem, or the definition of how hard the quantum computation is, will be based on the state that we try, say the bottleneck of the quantum computation is to build the initial state. And so estimating how difficult it is in a sense equivalent to estimating how difficult it is to do the quantum computational task. But of course, we will be using it for different purposes to study the behind the horizon regions of black holes. But that's where this field basically started. All right, in a very similar way to the way we define complexity of states, we can also define complexity of unitary transformations. Here we are going to try and multiply gates one after the other and build a unitary transformation that is our target unitary. If I'm still in the context of chains of n spins, the unitary transformation that rotate between the different states of n spins, leaving the group manifold SU2 to the n. And so the question of complexity becomes the question of give me a certain unitary in SU2 to the n, how many gates I have to multiply one after the other to get this unitary. So I start at the identity, and then I multiply unitary gates and try to get to a certain distance in this norm that appears here on the bottom right. A few interesting facts about the group SU2 to the n is that if I divide it to some epsilon-sized blocks, I would find that the furthest point in the group from the identity is at a distance which is exponential in n, and that the volume of this group, when I again divide it to epsilon-sized cubes, is double exponential in n. And these orders of magnitude play a role in the expected time behavior of complexity that I will talk about a bit later. Now, this definition is discrete, so that's not great from a number of different reasons. The first one is that we have this tolerance here, and we are very sensitive to it. So for example, one weird thing that can happen is that we want to get to a certain target unitary, but we missed by a little bit, like we are epsilon, like 2 epsilon size from it, a distance. And then we do another operation, and then we are a little bit still too far, and a little bit still too far. So we might like kind of circle the point, the ending point for a long amount of time or a long amount of steps before we actually converge to a distance epsilon. And that can present effects which are a bit ridiculous to our notion of distance. So that's one reason why we might be interested in a continuous notion of distance. Another one is that we are used to think about definitions of complexity in field theory and in gravity, which are continuous. And so a continuous definition is desirable also for this kind of applications. Right, so that's basically what Nielsen did for us. Nielsen proposed that we can translate the notion of distance by discrete counting to a notion of continuous distance by basically identifying the optimal circuits on SU2 to the n with certain geodesic distance that goes from the identity to exactly the target unitary that we are interested in. And in this game, the elementary generators of the group SU2 to the n, which are basically generalized products of Pauli matrices acting on the different spin, introduce motion in the group manifold, a motion that is continuous, so with continuous parameters. And then what Nielsen proposed was to define a metric on the associated Lie manifold and study continuous trajectories rather than a discrete one. And Nielsen used this to provide a bound on the discrete gate complexity. But basically, we will use it as our basic definition. All right, so that was just like some introductory comments about the notion of complexity. And now I will move to talk about the complexity in quantum field theory, both for pure and mixed states. Are there any questions?
As far as I can see, not in Potsdam. Most of this stuff.
Okay, very good. All right. So complexity in field theory. So okay. So one thing that I should say is, of course, complexity followed the opposite path than followed entanglement entropy, in the sense that it's a quantity in gravity which we are interested in, and we didn't have a definition of it in field theory until relatively recently, while entanglement followed the opposite path. It was known exactly what it is in field theory, and the gravity quantity was the thing which was conjecture. So here we are following the opposite path, and so the goal is to define it in quantum field theory. In order to do that, we need to choose a number of different things. We need to choose a reference state and target state. We need to choose a set of allowed gates, a measure for the length of a given circuit, so a distance function. We need to have a procedure for minimizing the circuit and finding the complexity. And one thing that is new in complexity in holography is that just like the entanglement entropy, complexity in holography is divergent, so we need to find a way to regulate it, and that can be done in various ways. Among other things, one can put a sharp momentum cutoff, or an alternative would be to put the system on the lattice. Right, so the system we started from was that of a free scalar quantum field theory, basically a simple Hamiltonian with defined in terms of momentum and field variables. And we focused on Gaussian states. And the state that we wanted to construct was the vacuum state. So basically, I'm going to keep track of the states that I'm building by looking at the prefactor of the two-point function. Since all the states are Gaussian, they are completely characterized by the two-point function. So keeping track of the coefficient of the two-point function in momentum space would be a good way to keep track of what's happening with the states. So here's a drawing of the coefficient of the two-point function, simply the momentum as a function of the momentum variable for the vacuum state, both in the case that is massive and in a case that is massless. And that's how it looks in position space. So basically correlations blow up at short distances. That's the reason that the complexity will be divergent, because there are very high correlations at short distances. Now the state I start with is the unentangled product state. So basically what I have to do is turn off the term in the Hamiltonian, which is responsible of the entanglement between the different sites. And I also allow for an arbitrary mass of this state I start with, which I will call mu. It will be the scale of the reference state. Now, if I draw the two-point function as a function of momentum once again, I will simply have a constant line. Or in position space, I will have a delta function. And you can see that every site basically only talks to itself. And as a consequence, the state is exactly unentangled. So the task that I want to do now is basically I want to take the constant, this kind of very simple unentangled reference state, and make it into the ground state. But as you see, I have to do it for infinitely many momenta. That's one way to view why the result is divergent. Right, so very good. So the way that we chose to regulate these divergences was to simply put a momentum cutoff and make the unentangled reference state into the ground state, but only up to a certain cutoff in momentum. A few more ingredients that I still need. One is the distance function. The distance function that we selected was the Fubini-Studi metric. It's a subset, can be viewed as a subset of the class of metrics considered by Nielsen with a particular choice of penalty factors. This particular choice is special in the sense that it throws away arbitrary phases in the state. So if I'm just modifying my state by an overall phase, I throw that away. And the complexity is the minimal length of this circuit. Now for the gates, what we did was to look at quadratic operators of that move us between the different Gaussian states. In particular, we focused on these three quadratic operators. BK is the operator that annihilates the state mu, so the reference state. And psi of sigma are the states that I move along the way in my circuit. Now, the wave functions, it turns, so okay, so here it naively looks like I have three directions in my circuit. That's a bit of a lie, because one direction is an overall phase, but I'm left with two real directions in my circuit. And so the state the states that I move through can be characterized in terms of one single complex function or two real functions encoded in this three-factor gamma plus of k and sigma, one complex function per momentum mode. And now if we use this trajectory of states in the Fubini-Studi metric, we will get the geometry of the Poincaré unit disk, for which the geodesics are known. And so it's very easy then to find that to go from the reference state that is exactly at the center of the disk to the vacuum state, which is along the radius, the real radius, one simply has to go in a straight line, and that gives an answer for the complexity, which takes the following form. So basically we have a volume law and then a subleading set of divergences in jumps of 2, where the leading divergence is proportional to lambda to the d minus 1. Lambda is the cutoff, and d is the dimension of space-time. So that's one higher divergence than one usually sees in entanglement entropy. And that prefactor depends on the choice of the reference state. And that matches well with holography. Okay. Now, the next step, so this was all about pure Gaussian states. The next step is to try and think how to define complexity for states which are mixed. So I'm going to focus on mixed Gaussian states, just to make the problem a bit simpler. And the idea is how to define the complexity for a state for which the density matrix cannot be decomposed in this way. So has different, say, weights to different states. And one definition that appears very often in the quantum information literature is that of the complexity of purification. So what one has to do is basically take the mixed state and try to purify it, so to give a pure state on a little bit more degrees of freedom, such that when you trace away the additional degrees of freedom, you remain with the mixed state that you are interested in. And so then one might ask, what's the minimal circuit that leads us from an unentangled reference state to one of these possible purifications of the mixed state? Now, the definition of complexity of purification is to try all the possible purifications of a given mixed state and minimize over those possible purifications and get the minimal complexity of the minimal possible purification of the given state. So I'm going to follow here a simple example. So I will start with an example of a simple harmonic oscillator with frequency omega. In this case, it turns out that the most general, well, actually with some, sorry, I get some notifications that my internet connection is unstable. Are you guys, can you guys still hear me?
Oh, we can hear actually very well.
Ah, okay, very good. Sorry. Yeah, I don't know. I just got this banner saying internet connection unstable, so I got a bit worried. Okay.
Let's see.
All right, so mixed states. So I'm now following the example of the single harmonic oscillator right, and I said that for a single harmonic oscillator, the most general mixed state with real parameters, so there is some restriction here, can be built from the thermal state. The thermal state has the following form, so it's basically this very symmetric sum over the energy eigenstates of the oscillator, squeezed from the right and the left with a squeezing operator, which is defined in terms of the annihilation and creation operators of the harmonic oscillator. So what this basically does is in position space representation, just rescales the coordinate. So that's the most general mixed state. It has two parameters, the temperature and the squeezing. Now it turns out that to purify it, since it's mixed, you need to add at least one more degree of freedom. And let's for a moment focus on the case in which you add exactly one more degree of freedom. Then the possible purifications, again with this small caveat that they are only with real parameters, take the following form. So they can be constructed from the famous purification of the thermal state, which is the thermophile double state. Again, constructed in a symmetric way, very symmetric way from two copies of the system from the energy eigenstate of the two oscillators this time. And then with the squeezing S1 of R, with the same R that I want to reach at the end for the density matrix. But then since I have an additional oscillator, it turns out that nothing changes if I squeeze the additional oscillator. So I actually have one parameter that is completely free in the extra oscillator. And now the complexity is basically, the complexity of the is simply the minimization over this S of the complexity of the purifying state psi1. Now, in general, these results, so the answer looks a bit long and is not very insightful, but I'm going to focus on two particular examples. The first one is the example in which the squeezing R is 0. So that's the thermal state. So I'm trying to purify the thermal state, and here R is also 0, but S is free, and I can ask the question, is the thermophile double the optimal purification, or is there a better purification with less complexity by turning on this S?
Sorry, Shira, a quick question here. Can you hear me?
Yeah.
Is there, I'm like, you put some restrictions on possible purifications, right? I mean, I can see why this is a purification of row 1, but it's not the most general purification of row 1, right?
Right, so I did put a restriction which is not extremely transparent in terms of these variables, and that's why I just mentioned it by words. So one thing that you can do is take another representation, right? You can write the density matrix in terms of what is known as position representation. So basically you dot it with a bra and a cat of x and x prime.
Yeah, sure. Yeah.
And then you want certain things from the density matrix, but it turns out that basically you have some free coefficient in front of the x squared, some coefficient in front of the x prime squared, and one in front of the xx prime. And then there is an hermiticity condition which relates two of them. So it does look like you would have two parameters, but these two parameters don't necessarily have to be real. And the reason they are real is an extra restriction that I did. So this actually, I'm lying by saying it's the most general. It's the most general with real parameters.
Okay, thanks. But I was more asking about the purification. Like, even if you start with this restricted density matrix, like, is it purification that you consider the most general, even within the realm of?
It's also most general with real parameters again. So it's again that I'm taking one extra. I mean, you could have something more general with complex parameters.
Okay, thanks. Yeah, I understood.
Right. Yes. Okay. So now I'm just going to focus on the thermal state because I think this state is very intuitive. Like we like it a lot. Also, we study it in holography. Right. So if I focus on the thermal state with R equals to 0, that's the answer. I mean, it's not particularly short or simple, but you can see the following thing. So mu is the scale again of the reference state where I started with. Omega is the oscillator frequency, beta is the temperature. This regime, if mu is very large, it's a very narrow regime of frequencies, somewhere in the middle range of frequencies, where the answer is one thing. And then in all other regimes, for example, for very large frequencies or very small frequencies, the answer is that thing. And this was a single oscillator, but of course, the way to move to a full bosonic free field theory is obvious. It's just to replace omega with the momentum dependent omega k, and integrate over the momentas. And so you see that this contribution is the one that is going to yield the UV divergences. So I'm going to refer to this term a bit prematurely as the UV divergences. Now, remember I told you that it's interesting to ask, since we always purify thermophile doubles with thermal states with thermophile doubles, especially in the context of gravity. If it's interesting to ask if the optimal purification of the thermal state is a thermophile double. And it turns out that the answer is most of the time, no. So we can separately compute, just set S to 0 and compute the complexity of the thermophile double state. And what we will find is that in this narrow band, the answer is yes. There is a narrow band of frequencies in which the thermophile double is indeed the optimal purification. But otherwise it's not, and it is much more divergent. It's a factor 2 more divergent. So this will the effect that when we study this in the full field theory, when we integrate over frequencies, the thermophile double will be twice as divergent. Right, so that's the next step. So the next step is to go to the bosonic field theory, replace omega by omega k, and integrate over momenta. And basically, as I told you, the thermophile double is going to be at least at the level of the leading divergence, twice as UV divergent as the thermal state. Now, the reason for this is because we are working extremely hard to do something we don't really need to do. The task that we are trying to implement is we want to build a thermal state. We are only using the additional copy of the field theory as some tool to do that, so that we can get the state out of being pure, so we can throw at the end these degrees of freedom of the second copy. But of course, if we work extremely hard to mimic the correlation of the copy, of the first copy in the second copy, we are building a lot of UV correlations in the second copy of the thermophile double that at the end of the day, we throw them away and we don't need them at all. So we are working extremely hard to do something we don't need. And that's the reason why it is not the optimal purification. Now, in particular, in holography, that's also the case, also in a very obvious way. So in holography, the divergences are due to the region near the boundary, and the thermophile double is dual to the two-sided eternal black hole, while the thermal state is this thing that lives on one boundary. And later on, I will talk about the holographic proposals, but there are holographic proposals for the complexity of subregions. In particular, when we focus on the right copy, these subregion complexity proposals gives divergences just from one side. And that means that using these proposals in holography, the complexity of the thermal state is really half the complexity, at least at the level of the leading divergence, half that of the divergence of the thermophile double state. So we see the same thing in holography.
I think it's only.
Okay. It's, yeah, a question. So this region there, that you described as a narrow band where the complexity is independent of mu or not divergent. So what is there any physical meaning of this region, or in what space?
Sorry, let me go back. You mean here?
Yes.
Yeah, I think the point is that you cannot really see a field theory which encodes only one of these regions. Like you see, it's basically encoding the different length scales of the theory. So it's some kind of middle range of length scales compared to the temperature, basically. So if you go to ranges which are very, very, very short compared to the inverse temperature, then you are building the vacuum and you don't care about the other copy. But if you are in some middle range of frequencies, then the thermophile double does the job for you of building the thermal state. It's, I don't know if to say it's the ranges in which it's more dominant to build it's more thermal rather than being more vacuum in certain ranges of frequencies or something like this. But okay, this bit and wavy kind of explanation. But anyway, you will see all different length scales in a field theory when you want to build a thermal state. Like you cannot chop just a certain range of frequencies. They will all exist. Right. Any more questions on this?
Like what you said about including, not including UV divergences fits also well with L1. I mean, you use L1 norm to it, right? It's like another indication that Colombia likes L1 norms.
Yes, I think that's true. Mm-hmm. Definitely. Yes.
Do we have more questions online?
Okay, that's fine. All right. So that's one type of special state, is the thermal state. Another type of special state that we are very used to studying is that of subregions of the vacuums. Take the vacuum state and we mod out a certain region. We remain with a mixed state on a subregion that I will call A. And so we study also numerically on the lattice purifications of this case. So basically this we did by putting everything on the lattice and putting completely arbitrary, or not completely arbitrary, but somewhat arbitrary choice of parameters in the purifying wave functions and minimizing over those. We did some studies on small systems that disclosed to us that it was enough to study purifications with exactly twice the number of degrees of freedom as in the systems that we are trying to purify. But then we made the conjecture that it was enough to focus on systems that have twice the number of degrees of freedom, at most twice the number of degrees of freedom as the system that we are trying to purify. And then basically we were working with very big matrices and doing numerical minimization. So we did this on the lattice in one spatial dimension. And what we found, so this is the results of the numerics.
Can I ask a question before that? So,
yes.
So previously, in the case of thermophile double states, like your previous peak transparencies, in field theory, you were using the fact that the state is translationally invariant, right? And that different momentum modes are, well, you were basically entangling, momentum modes at a given momentum with the purification, right? Over here, well, you get some density matrix that is not necessarily diagonal, right? So I think like you bring it into the form in which it's diagonal, right? And you purify modes, purify like entry by entry in this density matrix, right?
Yes, you're right. I mean, we are making a bit more than the assumptions I said. So we are doing two assumptions or two approximations. I mean, one of them is really an assumption, which is that you don't need more than twice the number of degrees of freedom in the subsystem for the purification. But we do make an additional assumption, or not assumption, approximation, which we saw was not so bad for small systems, small subsystems. Which is that we purify mode by mode. So exactly, so we take the density matrix and we bring it to a diagonal kind of form. And then for each mode, each mixed mode, we introduce one parameter. But then of course we rotate back to the original basis so everything gets mixed, but it's really a very, it's a not exhaustive subset of the possible purifications. We study roughly speaking, the number of parameters is more or less, roughly speaking, as the number of degrees of freedom in the system A. So while we could have had many more parameters because these are big matrices.
I see. Okay, thanks.
Yeah, also it was, because it's very hard to minimize with a lot of parameters anyway, so. But tests that we conducted on small systems, this was not actually optimal, but this was close to being optimal.
Yeah, so one question, Shira. Here you're using the L1 norm, right?
That's correct.
Did you also play around with the L2 norm?
Not so much. I think, yeah. Not so.
The results that you were quoting is similar as in other papers on the subject, in which one uses L2 norm to find the optimum and then evaluates the geodesic using L1 norm, or?
Yeah, so that's, yeah, so as you go back, we're also using previous results that in turn are also based on some assumptions or approximations, I would say, more than assumptions, because I think that it's not correct, really. It's just a good approximation. So, of course, one thing that you know, for example, is that this formula that we use for the pure states, both in our paper and in the paper of Ro and Rob, this log omega k over mu for the complexity of, say, pure states, is not really true if you optimize over all the possible gates, all the possible quadratic gates in the world. It's an approximation that you get using the L2 norm, and in the L1 norm, if you look at a certain subset of gates of momentums times field variables, then you can prove that it's optimal. But in general, you cannot really show, or I think it's even incorrect to say that it's exactly optimal. So more precisely, I would say that all these things are expected to be close to the real answer for the complexity from various tests on small systems. But that, strictly speaking, they only provide a bound.
Okay, thanks.
Right. Okay, so right. So here are the plots. So that's, as you said, the C1 norm as a function of the size of the subsystem over the size of the full system, and here you can see basically a linear trend. So what you see here is actually the leading divergence because all the rest are kind of hidden. And so you see that the leading divergence grows linearly with the size of the system. On the right, you see a plot as a function of the cutoff. So size of the system over cutoff for a fixed subsystem size. And so basically from these plots, you can extrapolate the behavior of how you expect the complexity to behave. And when you fit this, you find the following thing. So you find, once again, just like for the full system, some kind of volume law that is proportional to the size of the system over the cutoff in the leading divergence, and with a prefactor that depends on the choice of the reference state. Then you find a subleading divergence, which is logarithmic in the size of the system and a constant. Right. But if you are more careful, you can also try to see what's the dependence, for example, on the size of the subsystem inside the constant, and see if you can simplify it a little bit more. And by doing some fits of this sort, what we found was that the term that is logarithmic is actually taking this form by extracting the size dependence from the finite part. So it actually takes a form which is exactly proportional to the Cardy-Calabrese formula for the entanglement entropy. So that's kind of nice because it seems also from other works that the subleading term of the complexity is actually encoding something about the entanglement entropy.
So, sorry, just to understand a little better. So you're saying that if you combine like the last two terms that you're displaying, then they combine to precisely Cardy-Calabrese, or?
Yes, exactly, to something proportional to Cardy-Calabrese. So if you actually leave here the constant, so here, when I say constant, cutoff independent, but could depend, for example, on the size of the system. But if you make the extra effort to remove the size of the system from here and really leave it a constant, like pi over 8, I don't know, then you can see that the size of the system dependence, like this L, big L, small l, whatever, recombines into the log, and then when you are really left with a constant that doesn't depend on these things here, you will see that pops out the Cardy-Calabrese formula in the log.
So in the story of entanglement entropy, like the universal piece of entanglement entropy in multiple one dimension is C over 3, right? Like it encodes C. Like, would you also be, I mean, otherwise, like in the context of discussion of complexity and universal pieces of complexity, this would be also universal complexity, right?
So I think, so I didn't write it, and now I don't remember exactly, but I'm pretty sure that the coefficient here actually depends also on the reference frequency. So here I did not extract, so this still depends on reference frequency, and this in principle could depend on reference frequency, not sure how. But I'm pretty sure that this guy does depend on the reference frequency. So I think if you manage to understand how, then you would be able to read C for me.
But the reference frequency is dimension full, so it's like mu times L that you mean.
Yeah, from this sigma ref in this sense.
Oh, okay, good.
Okay.
Thank you.
Right. Yeah, actually, that's so that's the part about the mixed state. But I think we did not have enough. I think it requires more study to exactly identify the dependence on the sigma ref, etc. But I think that's actually it's nice and maybe also in a sense expected, because I think the point is that you expect that there are not that many numbers in the vacuum. So those that you can extract are basically the central charge. So I do think that unless you start going to dynamical situation, and then you have scrambling time and the Lyapunov exponent and whatnot, but as long as you are in static situation, you do expect that all the things eventually are just going to depend on the central charge.
This is really interesting because this is a comment. This is really interesting. It's like this would be like some sort of how complexity carries universal information about underlying CT, right? It looks a bit like this. It would be very nice.
Right. No, I agree. I think so too.
Yeah, super. Thanks.
Okay, very nice. Okay, so next part is short, I think, yes, is about holography. So in holography, the systems that we are studying are very, very different compared to those that I was telling you now, that are like free bosonic field theories. They are what's known as fast scramblers, so systems that spread the effect of localized perturbations over all the degrees of freedom in a time which is logarithmic in the entropy. And for example, these would be, for spin chains, Hamiltonians of this form with generic values of the coupling J are expected to be fast scramblers. Now, for fast scramblers, you remember this picture of the gauge group. The largest distance was exponential in n, and the volume was double exponential. We can look at the complexity of this specific operator, that is the time evolution operator, and the complexity of this operator is expected to follow the following pattern. So at early times, we expect to see not a lot of cancellations between different gates. So complexity will grow linearly for a while, until a time which is exponential in n, so until you reach kind of the end of the gauge group. And then it will circle around this, this maximal complexity for a while and eventually dive back down. Now, in holography, there are two proposals for the complexity of a state. The first one is the complexity equals volume conjecture, time the complexity to the volume of a maximal slice anchored at the boundary of ADS where the state is defined. And the second one ties the complexity to the gravitational action of the Wheeler-DeWitt patch, which is basically a null bounded region, also anchored at the boundary in the place where the state is defined. Right, and for example, if we look at divergences, in holography, the reason for divergences I already mentioned is the region near the boundary where the metric blows up, and the standard way of regulating that is putting a cutoff at z equals delta in a Pfefferman-Graham expansion. So if one does that, for example, for vacuum ADS, we can evaluate these divergences, and what we find is a behavior that is very similar to what we saw earlier in the case of the free field theories. So a divergence which is basically a volume law with the right power of the cutoff, delta to the d minus 1. Using the action proposal, there is a certain refactor which depends on the choice of null boundaries or normals to the null boundaries. And that choice looks very similar to the way that in field theory was the influence of the choice of reference state scale. Right, another thing that is special to holography is that the result is proportional to the central charge, which in the case of the free field theory we didn't have because it was an order 1 number. Right, so now going back to the growth of the interior of the black holes, here's the Penrose diagram of an eternal ADS black hole. That's the direction of time. And every point in this diagram is a sphere. So basically, if I look at the maximal volume slice, which connects the two boundaries, so basically the place where the thermofield double state is defined, the one that is dual to this geometry, I will see some kind of corridor like that, that is the wormhole. And as time goes by, the wormhole gets longer and longer. And that was basically our original puzzle of how the growth is encoded in the boundary and led to all this idea of complexity. So you saw also from the circuit picture or from the general expectation for the fast scramblers that this is also expected to be indeed the behavior of complexity. Now, why do we think that that quantity, volume, and action are complexity? So there are 3 reasons. The first one is more heuristic, is the idea that ADS space is actually a representation or a visualization, can be seen as a visualization of the way we build entanglement in a state. So actually it looks very similar to a tensor network which constructs the state. And that's an idea due to Brian Swingle in 2009. And in this picture, the number of gates is simply the geometric volume. The second reason I already told you is this linear growth at late times. It's expected from complexity of fast scrambling system and is also seen by the volumes and the action in this geometry. And the third reason, the one that I find most convincing, is the one related to the effect of perturbations on complexity. So in order to study the effect of perturbations on complexity, one usually looks at this operator that is known as the precursor, which includes a backwards time evolution a single qubit perturbation and a future time evolution. And estimating the complexity of this guy basically tells us how the complexity is influenced by, of a system is influenced by the perturbation inserted some time t in the past. So if there was no perturbation, this future and past time evolution would cancel and the complexity would be 0. But since there is a perturbation, then the complexity will actually grow with time. So let's see what happens. So imagine that the unitary evolution is most efficiently constructed by a sequence of gates, G1, G2 through Gn. That's the perturbation, and that's the backward evolution, so with exactly the opposite kind of gates. And now I want to know what's the complexity of this operator as time evolves. So at early time, I just have a small number of operators on the left and on the right, and as time evolves, I have more and more. All right, so now things start depending on whether the perturbation commutes or doesn't commute on the gates which basically appear in the time evolution. So if the gates do not commute, we get a complexity that is increasing. So I started with complexity 1, that was just the complexity of the perturbation. Now I have complexity 3. Now, if I have a gate that does commute, I can construct the operator without putting it at all. And so the complexity is still 3. Now it's 5. Then another gate which commutes doesn't contribute to the complexity, one that does. And at this point in time, once the whole system has been, you would say, infected.
Don't use these words.
yeah, I know, it's pretty, with recent, yeah. What can you do? Let's hope that we will only have infections in complexity. Yes, so once the system has crumbled the perturbations, basically now things start accumulating and the complexity will grow linearly in time in a rate that is twice as big as would grow for the original operator because everything accumulates, at least until very late times when accidental cancellation starts again. So that's what's expected. So it's very easy to build a statistical model for this evolution of complexity if the spin chain is large, and that's what you would get. So you would get that the complexity grows in time in the following way. That's a formula that can be written, just write the differential equation for the probabilities and so on. And it has two regimes. So at very early times, times much earlier than what's known as the scrambling time, there is a behavior which is exponential. I should actually define all the letters. So N is the number of spins, L is a time step for the application of a single gate, and T star is what's known as the scrambling time. It's the time until the whole system was basically scrambled the perturbation and things started growing linearly again. So at early time, exponential growth with a big suppressing constant prefactor, since T star is big, and at late times, we go back to linear growth, so that's basically the behavior that you expect. Exponential growth followed by linear growth for the complexity of the precursor. Now in gravity, it's possible to mimic a very similar configuration by injecting a shockwave into a black hole. In terms of the geometry, this is like a black hole of a certain size, pasted together with a black hole with a slightly higher temperature. And then one can compute simply volumes and actions in this geometry to see how the complexity depends on the time in which the perturbation was injected, which is the time of the precursor. So here are some plots of the complexity as a function of the time of injecting the perturbation. And this is for very light injections, so for a small change in temperature of the black hole. And what you see is that there is a certain time in which the complexity deviates and from this, like kind of say, exponential and becomes linear. This time can be fitted and found to be given by this equation, which depends on the temperature and the increment of temperature, and is very famously known also from other calculations to be the scrambling time in holography. After the scrambling time, you see that the complexity grows linearly at twice the rate that it would grow just by the usual time evolution of the system.
Shira, do you see differences here between the two conjectures, or it doesn't matter really which one you pick?
No, really just only in the, so you see, like you remember probably that from the action, the prefactor is 2m over pi. So the equation I'm giving you here is for the action, but you get exactly the same for the volume with a factor of 2 compared to the growth rate of the volume. So all these kind of properties that are related to the perturbation, except for, you know, the overall prefactor of the late time growth that is overall rescaled everywhere, it's exactly the same. Like you can read the same scrambling time. In a second, you will see that you can read the same Lyapunov exponent. They behave exactly the same.
Thanks.
Right, so I told you that this was actually an exponential regime. It's very hard to see because it's suppressed by a huge coefficient. But the way to see it is you differentiate this plot. So this will then become a constant. This will become a constant, and then, but this will stay exponent, and then you will take the log. So then this will become linear. And that's what you see. So this basically the log of this derivative that I told you. And so that's actually showing that at early times you have this exponential regime that you can fit, and you will find that it's actually following the formula from before with the scrambling time suppression as expected, and with the Lyapunov exponent for maximally chaotic systems. Right. So you can repeat the same kind of exercise for heavy shocks. You can also repeat the circuit argument, and you find a perfect experiment. So here I'm just showing you the gravity results for heavier shocks. So when you add a perturbation that is a significant portion of the black hole temperature. And one thing that changes is that when you throw on the black hole a lot of, say, you change a lot the energy of the system, then it takes a very short amount of time to scramble, a time that is of the order of the inverse temperature. And you expect the complexity to grow at early times with the rate which is proportional to the difference of the two masses, and at late times at a rate which is the sum of the two masses. And this is a plot of the derivatives, and the dashed line basically show you the expectation, and you see that it starts exactly where it should, ends exactly where it should. So this basically exactly in accord with expectation. Right, so I'm basically done. Let me just conclude. So I told you about complexity, that is this very interesting new set of measures in quantum information that can teach us about the interior of black holes. We defined complexity in quantum field theory, both for mixed and pure states. We studied a bit the time dependence and the effect of perturbation, and saw that we can diagnose scrambling and chaos in quantum field theory by using this quantity that is complexity. And so of course, there are many things to do that are left. I think the biggest question is to try and define complexity in strongly interacting systems, both in perturbation theory or using conformal field theory techniques. Another point that is maybe interesting is to see whether our understanding of, say, bosonic quantum field theory in simple situation can be used to maybe construct a different kind of quantum computational systems, which are usually used with qubits at the moment. And then there are more, say, theoretical questions about the structure of holography. Where is the information about the interior of black holes stored? How does all these stories of the complexity relate, for example, to new ideas about black hole evaporation and so on? And in general, how can complexity help us to understand better the bulk boundary map? So there's lots to do, and that's it.
Super, thank you, Shira. I have quite a bit of questions here in Potsdam. Are there any more questions here or online? exhausted our mind power for this. Any questions online? No, I think that's it. Okay, thanks.